Okay, hello everyone. This question, I think the next one I received from students. I remember this was a maybe midterm question previously, a few years back. I think at the start of the COVID, I think, if I remember. Okay, so this question is about Gauss law, but you will see from the solution it's not very straightforward because it includes integration on both sides of the Gauss law. So let's read it. So we have a long insulating cylinder with radius A, 9.3 millimeters, has a non-uniform volume charge density ρ. Ρ is given as beta multiplied by r squared, where beta is equal to 2.2 millicoulomb divided by m to the power of 5. R is given, it's a radial direction, obvious from the center of the axis of the cylinder. Find the magnitude of the electric field at a distance r, 3.2 millimeters. So it looks like the distance is inside, right? So this insulating, it's a charge. Charge is distributed from inside and to outside. Okay, so in order to proceed, we need to use Gauss law. So integration, full integration of E dot dA is equal to Q enclosed by the Gaussian surface or inside divided by epsilon naught. Okay. So we need to come up with a Gaussian surface. Well, we have done questions like this before. So Gaussian surface here is a cylinder with a specific length, let's say L, and radius of R. Okay, so this is our Gaussian surface. This is our Gaussian surface. Okay, so the challenge is to find the Q inside this Gaussian surface. The Q inside this Gaussian surface. Left-hand side of the equation is not difficult. Left-hand side of the equation, let's call this one 1. Let's call this one 2. Let's do it piece by piece. So let's do the left-hand side, which is 1. Basically, we know there is no flux on the top surface of the cylinder. There is no flux at the bottom surface of the cylinder. There's only flux from the side of the cylinder because the electric field and dA of the side, the angle between them is 0, right? But there is no electric field that goes, upward or downward. So there is no flux to the top surface, lower surface of the small cylinder Gaussian surface. So basically the left-hand side is simply equal to E integration of dA, which is the side of the small cylinder, which equals to E. The dA here, the total integration is 2 pi r multiplied by L. So this is left side of that of equation 1. This is left side of equation 1. So now we need to find the right side of equation 1. So the right side too is simply we are trying to find Q in the Q inside the Gaussian surface divided by epsilon. Okay, this equals to. So we will find the Q using density. We know that density is equal to dQ divided by dV. Means dQ is equal to ρ multiplied by dV. So what do I mean by dV here? dV actually is a volume of a small cylindrical shell. When I say cylindrical shell, I talk about the following things. Look at this cylindrical shell, something like this. This is cylindrical shell. It has a volume because this is an area. This is R, and that small distance is dr. So the dV simply is equal to 2 pi r dr. This is area. You multiply by L. So this is dV. Okay. Now, in order to find Q inside, so you need to do integration. Okay. So by doing this integration, the left-hand side is simply Q in equal to the right-hand side. We know that ρ is given by this equation. Okay, so you need to substitute that. is equal to beta r squared, and our dv is 2 pi r drl. Okay, and of course the integration is with r, so we have r squared, r mean r cubic. The limit of integral is from 0 to r, small r, because we need actually to do, we are trying to find the q inside this cylinder, so we go from 0 to r. That integration is simple. Basically it's going to give us beta constant, 2 pi constant, r with r square is r cubic, so it's 1 over 4 r to the power of 4. Okay, so basically we need to divide this right by epsilon naught. Let's not forget epsilon naught. So let's divide by epsilon naught. Now we need to equalize this. So this is the right hand side of the equation. Let's write it. Right side of equation 1. Okay, so the final answer is this should be equal to that. So E multiplied by 2 pi RL equal to beta 2 pi R4 and then 4 epsilon naught. I think 2 pi RL will simply cancel out. 2 pi, where is L? I forgot L. Here I forgot L, right? Here. So here there is L. With L, and this is 3. So the answer basically will be equal, E will be equal to what? Beta divided by 4, beta divided by 4, and then R to the power of 3. Okay, I'm not going to do the very last step by substituting numbers. We have beta and we have R. So this should be the final answer. Okay, so the difficulty was actually finding the Q inside the Gaussian surface. So that was one question of a previous midterm. Okay, let's go another one. Here we have a long conducting cylinder charged with a uniform charge density. This one is a uniform charge density, which is lambda. An electron moves in a circular path at a distance r is equal to 25 centimeters from the center of the cylinder. Find the speed of the electron in meter per second unit. Lambda is given. I think lambda should be negative in order to the question to make sense. I'll explain. Should be negative. Because if the cylinder is negative charge, the electric field will actually, at this point, the electric field will go toward the cylinder. At any point on the path of the electron will be, actually, no, this is electron, so my mistake. This is correct. This is correct. Okay, so it's actually positive. Because if it's positive, the electric field at this location will go this way, and this location will go that way, this way. So the force, because this electron, the force will be to the center of this circle. So let me draw it like this. So electron here, there will be a force on the electron that goes to the center. Here it goes to the center. So it's basically centripetal force taken in physics 1. But that force basically is equal to Q of electron multiplied by the electric field. Okay, Q multiplied by electric field. Okay. So the question asks for find the speed. Well, this is centripetal force. So we know from physics 1, Fc is equal to mv squared divided by r. But Fc in this particular question, Fc is equal to Q multiplied by E. So we have this equation. We could find velocity here. How many unknowns we have? We are looking for velocity, but we need also electric field to find electric field. And to find electric field at a point outside here, it's easy. We have done this before. Okay. So before we do that, let me just rearrange the equation. So V is equal to Q E R divided by M So that will be the answer, but we have a problem, as I said. We need to find this electric field first. So we need to use Gauss law to find this electric field. Okay, so E dot dA is equal to Q inside divided by epsilon naught. So this is our cylinder. This is our cylinder. We want to find electric field here. We're gonna make another cylinder. Big cylinder. It's a Gaussian surface. So now this is our Gaussian surface. This is easier than the previous example. Left-hand side will be similar to the previous example. So it's equal to E 2 pi. Remember, this is for the Gaussian surface, right? So it's 2 pi small r multiplied by L. I should say this is L. Okay, equal to the amount of charge located inside the big cylinder. The Gaussian surface. The Gaussian surface is equal to lambda multiplied by this length. Right, multiplied by this length, which is L, divided by epsilon naught. Okay, so this with this will cancel out, and electric field basically is equal to lambda divided by epsilon naught, and we have 2 pi r. So it's gonna be something like this. Okay, so you need to this one here. I have one small mistake. If you remember from the top, this should not be r, right? Because the electron is going around small r. By mistake I put r, so let me correct this. It's actually small r, which means this will be small r. Okay, small r. So remember, you have 1 r here and 1 r there. There will be some cancellation. Let's do this. So V is equal to Q. E is this bunch of parameters, 2 pi r. What else? We have R and M. We have R and M. So R with R will cancel out, and I think that's it. And we have all the information, right? Okay, let's see which is which. This is charge of electron, 1.6 10 to the power minus 19, right? Lambda is given. Epsilon naught, 8.85 10 to the power minus 12. 2 pi, and M is the mass of electron. Also, the question should give you that. So this is 9.1 10 to the power minus 31. Okay, this Q is 1.6 10 to the power minus 19, and you have lambda, you have everything, so you could find the value of velocity. Okay, another question. When a potential looks like something different, right? When a potential difference of 1.38 volt is applied on a plate to the plates or parallel plate capacitor, the plates carry a surface charge density of 39 nanocoulomb per centimeter square. Find the distance between the two plates. Wow, let's see what this question asks for. So we have delta V equal to 138 volt. We have surface charge density, which is sigma, equal to 39 nanocoulomb centimeter square. We have a parallel plate. Well, let's see how we could solve this problem. Few things for parallel plate. So we know Q is equal to CV, C delta V, okay? C delta V. So, okay, we have this guy here. Also, this is a parallel plate, so we know C is equal to epsilon naught A divided by D. So it looks like we are looking for this. But none of these so far makes sense because we don't have all these parameters. But there is one more thing. Surface charge density is given. we could relate the electric field inside the plate. So if this is positive, this is negative, we know there is electric field, right? If I remember, and you should also remember that electric field inside paraplate is equal to sigma divided by epsilon, not 2, remember. If you put 2 here, it's for one plate, we have 2 plates, so sigma divided by epsilon naught. Okay, so things now, wow, too many equations. One more thing. So the knowns, I'm going to put like a, yellow color means we have, the green means we don't have. One more equation I think we have here. Delta V is equal to E multiplied D. Okay? So let's combine all those guys. So what should we do? What should we do? Okay, let me see. So instead of E, I'm going to put E delta V divided by D. So this equation, I'm going to just change it. I'm going to make it like this. Instead of E, so it's delta V divided by D equal to sigma epsilon naught. Oh, it's looks like we got it, right? Yeah, so we get the answer. So D is equal to epsilon naught delta V epsilon naught delta V divided by sigma. So it looks like we didn't need the first 2 equations, but I didn't know the solution first, so I have to put all the equation in front of. So we don't need actually the first 2, because E sigma divided by epsilon naught delta V is equal to ED. E is equal to this. Yeah. Okay. We have epsilon naught, we have delta V, we have sigma, so that was cool. Okay. Okay, another question on capacitors. How much energy is stored in the 50 microfarad capacitor when VAB is equal to 22 volts? So it asks for the energy in that capacitor. I usually like to name those, so C1, C2, C3, right? Okay, so we have the delta VAB. It's over here, between these 2 points. So first thing, let's find the C equivalent. So C equivalent, these are series connection, right? Series connection. So basically is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Equal to 125, 50, 25, so 25, 25, 50. You could take 50 as a common. Basically, this is 10 microfarad. 10 microfarad. Okay? Now, we could find the Q equivalent or Q total. So Q total is equal to C equivalent multiplied by delta V. And this equal to 10 micro, so 10 minus 6, multiplied by 22, so it's equal to 220 micro column, right? Let's write it like this. Because these are series, what happened in the series? Yeah, because these are series, we have the same charge, right? It's a series connection, so we have the same charge accumulated. So means Q total or Q2 basically is equal to 220 multiplied by 6 column. Okay, so energy, we could find it U2 is equal to half CV square, or basically just say half Q square, Q2 square divided by C2. So it's equal to 1 over 2, 220, 10 to the power minus 6, we square it, And then C2 is 50, right? 50, 10 to the power minus 6. So this should give you some joules.